The heart of Mars just threw scientists a curveball. Our entire picture of what's going on under all that red dust might need a rethink. What happened? NASA's InSight lander has turned up a revelation at the very center of Mars. The planet's inner core is solid, not soft and mushy, as almost everyone believed. That's right, where researchers had long expected a gooey center, they found a hard, solid one roughly 600 kilometers, 373 miles wide. And this is the part most people miss. Not only does it challenge previous models, it completely contradicts the current scientific consensus that Mars's core should be too hot and full of lighter elements to crystallize into a solid. As Huixing Bi and fellow seismologists at the University of Science and Technology of China explain, earlier theories insisted Mars's inner core would stay liquid because of all its sulfur, oxygen, and carbon. These lower the core's freezing point, so the core should stay soft with all that heat.
So what's going on here? Is our understanding of planetary evolution off track? Let's pull back. Until just a few years ago, the hidden layers under Mars's surface were, well, a mystery. The breakthrough came via InSight, a 4-year mission, 2018 to 2022, where a sensitive seismometer listened to every quake and cosmic collision rippling through the Martian crust. Using those vibrations, scientists mapped out the inside, a rocky crust, a molten mantle, and a compact core, not unlike Earth's own anatomy. But here's where it gets controversial. Mars has no global magnetic field these days, just patches in its crust that hint at a magnetic past. On Earth, the engine behind the planet's magnetic shield is a constantly convecting, partially solid core. But Mars seems to run by different rules. Earth's seismology depends on data from many locations. Not so on Mars. InSight had just one vantage point. Instead, scientists got creative. They analyzed quake waves from 23 especially clear impact events, using techniques usually reserved for combining signals from many sensors on Earth. This clever workaround let them spot seismic waves bouncing through Mars's center. These waves, by their timing and paths, pointed right at a solid inner core. So how do these waves tell the story? Consider the terminology. P waves race through the mantle and crust. They're the speedsters. K waves traverse the liquid outer core. I waves punch through the inner core, and little I marks bouncing off its boundary. A wave designated PKIKP, for example, zips through the mantle, crosses the outer core, bounces off the inner core, and races back out. When Bi's team saw multiple varieties of these inner core crossing waves, not just one, they knew their discovery was rock solid, pun intended. Even more telling, the timing of some waves, like PKKP, arriving early, backed up their findings. Their models even predicted a new type of wave snaking through Mars's inner core, spotted in the data as well. So where does the debate begin? How can Mars have such a solid inner core if the temperatures and chemistry should keep it flowing? Answering this mystery may force planetary scientists to re-examine their models of how heavy and light elements mix and separate under incredible pressure and heat. This research isn't just about Mars. It reshapes our grasp on how rocky worlds, planets most likely to host life, evolve over billions of years. As Bi's team points out, working out the size and makeup of Mars's inner core gives us crucial clues to the planet's thermal and chemical history. If Mars once had a dynamo-driven magnetic field, as crustal magnetism suggests, what does that say about its long, mysterious transformation? This also stirs up debate. If Mars's core surprises us in this way, could our ideas on other planets, including those circling distant stars, be just as mistaken? What if our core-centric principles about habitability and magnetic fields need to be rewritten? So here's the burning question. Does Mars's unexpected core mean our understanding of planetary formation is flawed, or do we need to consider even wilder possibilities? Where do you stand? Are you convinced by the seismic evidence, or do you think there's another explanation? Jump into the comments and let's hear your perspective. Should science double-check its assumptions? Or is this just one fascinating exception to the rule?